All right, so this video will have the similar problem to what we did in class, but extended a little bit, and so can go through it a little bit more carefully um, and make some more general statements about Couette flow, which is generally speaking is just steady laminar. So laminar allows us to make some of these assumptions that I'll talk about here in a second, but it's viscous flow, but it's highly viscous flow. So we're in a regime where things are well behaved. But it's laminar flow between moving plates, parallel moving plates. So this is the system here in general. We have a top plate moving with velocity u, bottom plate is fixed, and this would be the velocity profile we've seen in the past. Gravity acting downward. Here's our xy xy coordinate system labeled here, and the height of the between the two plates is b. So we just have a plate being pulled on the top, and it generates this velocity profile. You said, well, this is what we've seen before, and implicit in all our assumptions before was that there was no pressure gradient along the x direction. And we'll see here if that we do get a pressure derivative or a pressure change along the channel, this linear profile is no longer true. The simplifications we can make is that this is a steady system, just kind of how we define it. And at some point, as long as we haven't gone from a transient of a fixed state to the plate being moving, then the steady assumption is completely valid. So it's steady, that there's flow only in the x direction, and this comes from this laminar assumption, so it's well behaved, and that there's flow only in the x direction. And the other is that it's a 2D flow, meaning that there's no flow, not only no flow in the z direction, so in or out of the page, but also that there's no changes in the z direction. So any slice you look at here is going to look the same into and out of the page. Okay, so as we start here, we look at our continuity equation, so the differential form of the continuity equation, and we need to cancel out the appropriate terms here. And the appropriate terms to cancel out, well, we haven't said anything about changes in x, and we haven't said anything about the u velocity. We don't, that's kind of our unknowns about the problem. But we have said that v equals 0, and we have said that w equals 0. So all we're left with here is that du dx is equal to 0. If we then go to the Navier-Stokes equations, the momentum equations, right, so this is the full form. But a lot of these terms go away, and in fact, the whole left-hand side should go away, and that's allows us to still use the full Navier-Stokes equations, but be able to say something about this system, right? So these are the nonlinear terms, these three right in here. All right, so because of the steady assumption, this first term goes to 0. From continuity, this term goes to 0. Our v velocity and w velocity are both 0, so these terms go to 0. This pressure gradient in the x direction, this is what we have up here. This is true if dp dx is 0, but none of our simplifications allow us to say anything about this term. Our gravity is in the downward in the y direction here, so there's no x component of gravity, so that term goes away. Now we get into our viscous shear stress terms. This first one has a du dx inside, so it goes to 0. We also said that changes in z go to 0. It's a 2D flow, so all we're left with here is the dp dx and the second derivative of u with y. Right? We can do something similar for y and z, but here's our result from the x momentum equation. 0 on the left-hand side, we have our pressure derivative plus this one viscous term, which is the second derivative of u in the y direction. Our y momentum, if we did something very similar, again, the left-hand side would go to 0. This dp dy for the y momentum equation, we wouldn't be able to say anything about that, but our body force term is non-zero, right? So the g is completely in that y direction. Okay. But these three terms here will look like they'll be, instead of u for our y momentum, these will be v's, and we know that v is 0, so v is 0 everywhere, then all of its derivatives are 0, so those all go away. So all we're left with in our y momentum is dp dy and rho g. Well, if we integrate that, well, first let's jump down to the z momentum. If you do all the same things in the z momentum, the same thing will happen. I mean, we already know that changes in the z direction should come to 0. Well, the only term that's left over is the dp dz, which is equal to 0. So this is a result of the z momentum equations, the z component of the Navier-Stokes equations. And so that matches what one of our assumptions is. So that's good. But specifically, this means that pressure is not a function of z either. Right? So it's implicit in the assumption here, but the result that we find is that pressure is not a function of z. If we go back to our y momentum and integrate this once, we're left with that the pressure is minus rho gy plus some function of x. And the reason this isn't a function of x and z is because we just found down here that pressure is not a function of z. Okay, so pressure is a function of x, and then added on the function of y is a hydrostatic term, right? So this is the hydrostatic pressure that we've talked about in the past, plus perhaps a function of x. So it could change in x, but its change in y is hydrostatic purely, and its change in z is nothing because it's in the horizontal here. So in y and z, pressure acts like it's a hydrostatic, but this extra x dependence is going to deviate it from. We could, in general, make a deviation here from hydrostatic pressure. However, the result here is that dp dx, right, if we take the derivative of pressure with x, right, and go up to here, this term drops away, and we're just left with, it's just the derivative of this f, whatever this extra function, the extra dependence on x is. So it means that the gradient of pressure in x, the derivative of pressure in x, is not a function of y. It is only a function of x. Okay, so that's going to be important as we go forward here. Okay, so we're going to take again the result from our x momentum and integrate it twice. So we pull the pressure gradient to the other side, so dp dx, and divide through by the viscosity, and we're left with this differential equation here. Well, this is on the left-hand side. We might want to integrate this in y, and we're going to have to integrate it twice. But we know now that, well, first of all, our velocity can only be a function of y. Right? We've said that there's no derivatives in z, and du dx is 0. So that means that u is not a function of z, and u is not a function of y. U can only be a function of y, and so that these partial derivative up here in y is now an absolute derivative, a total derivative in y. Okay, so u only is a function of y. That's one thing to note. And then again, our notice here that dp dx is not a function of y allows us to treat it just as a function of x, and therefore when we integrate it once, we just hit it with 1y and an integration constant. We integrate again. This y now goes to y squared over 2, and our first integration constant now is linear, and we now get a second integration constant. Okay, so here's our general form for that velocity profile. Right? These two parts here make it a linear profile, but this dp dx, which is hidden in here, dp dx is just f prime of x. If we have a dp dx, it actually starts to have a quadratic nature to it. Okay, so that's the general form. Now let's solve for these. Let's solve for these integration constants using boundary conditions. Our boundary conditions, we're going to need 2 of them to solve for the 2 integration constants, right? And that can just come from the no-slip conditions. That is that our velocity at the walls must match the velocity of the walls. So our velocity at y equals 0 at the bottom is just 0 because that wall isn't moving, and our velocity at the top is this big U. Okay, and these both come from no slip. The velocity must move with whatever wall. So if we do the first one, plug in y equals 0 to our equation here. That goes to 0. That goes to 0. U at y equals 0 must be 0. Therefore, C2 is just 0. All right, simple enough. Good to get rid of one of our integration constants. The other integration constant doesn't go away. Here we have the velocity at y equals b, so at the top wall is the velocity of the wall, big U. Plug that in, we have big U for our u of y, evaluated where y equals b. So here our y squared goes to b squared, and we're just left with c1b over here. Solve for c1, so pull this term to the other side. Pull this term to the other side and divide through by b to solve for c1, and we're left with this form. When we plug it back in to our general form of the velocity, this is what we get. Okay, so this says that here's that linear portion, right, that you would expect if dp dx is equal to 0. Okay, we'll get into that in a second here. But, so if we plug in dp dx equals to 0, okay, this will be the first case we'll consider. If dp dx is equal to 0, our u of y is just a linear. It's just uy over b. It's just a linear function of y going from 0 up to then when we plug in b, we just have big U. Okay? Now, if dp dx is less than 0, right, this is then a negative term, and we, well, this is now negative, and our parabolas start to look like this, right? So what this means is that we have additional acceleration because there's a pressure drop as we go forward in x. Remember that our x is in this direction, and our y is up. But this means that the pressure will decrease as you go along the channel between these two plates, and that pressure drop that the fluid experiences will then generate an acceleration in certain regions, but it must still stick at the two walls. If instead the pressure gradient is positive, so now the flow is going into a higher pressure region, there's going to be a resistance to the flow which acts like a drag on the velocity profile, and actually you can get a backflow in certain regions. But again, the flow sticks at the 2 points. Okay, so the special case, if dp dx is equal to 0, we just get this linear profile, as we said. If instead velocity, the velocity of the top plate is 0, right, so that we're going to bring this back to just 0, well then we're just left with that the velocity profile in y, so basically this first term just goes away, and we're just left with the quadratic term, right? Well, this is a parabola where the velocity is 0 at both the top and the bottom, at both y equals 0 and y equals b, and so it looks like this, right? So that's because the two, setting this equal to 0, your two roots is just y equals 0 and y equals b, right? Okay, so we know we have a parabola. In this case where the top plate isn't moving, let's determine the volumetric flow between the plates. This volumetric flow we can just determine by integrating the velocity over 0 to b in the y direction. Doing this integration, our y squared term becomes cubic, our y term becomes y squared. Plug in our bounds from 0 to b, and we're just left with that the volumetric flow rate is written like this. So we have a b cubed over 12, and then on the bottom we have viscosity, but then dp dx is here. So our volumetric flow rate is related to minus dp dx. Okay, so in order for the flow to be in this direction, so for a positive volumetric flow rate, dp dx must be negative, right? And that's because we want a positive quantity. The only thing here that can be negative is dp dx. So that means there must be a pressure drop as the flow proceeds. And that is caused or supported or caused by the viscous shear forces experienced at the wall. So there's viscous drag here pulling on the flow, forces in that direction being balanced by that pressure drop as the flow goes along.